about Dr. C. Gnanaseelan. He is Scientist G and Project Director at Indian Institute of Tropical Meteorology, Pune. He obtained a PhD from IIT Kharagpur. He has published more than 125 research papers in peer-reviewed international journals and edited 2 books. He has successfully guided 15 PhD and 30 master's theses and currently guiding 50 PhD students. His areas of research include physical and dynamical oceanography, monsoon modeling, climate variability, decadal climate prediction, ocean modeling, Indian Ocean variability, ocean data assimilation, etc. He received several honors such as Adjunct Professor of University of Pune, Visiting Fellow of University of Hyderabad, and served as visiting faculty of IIT Delhi, IIT Bhubaneswar, and many universities. He has also received many awards such as Young Scientist Award of Ministry of Earth Sciences, Golden Jubilee and Silver Jubilee Award of IITM, Platinum Jubilee Lecture of Indian Science Congress Association. He has been teaching oceanography to MSc and PhD students for more than 22 years now. So we are really fortunate to have a person with such high achievement among with us today. So without spending much more time, let me welcome Dr. C. Gnanaseelan, my PhD supervisor, to deliver his lecture today. The floor is all yours, sir.
Thank you, Dr. Sayandini. Today I'm not seeing any participants. There are very few, right? So they will be joining this.
Yeah, no, there are quite like our students have already joined, sir, and then you can start. Maybe they will be joining slowly.
Okay.
Yeah.
Okay. Can you see the slides?
Yes, sir.
Okay. Thank you. Okay. Thank you, Dr. Sayandini, for the nice introduction. And in fact, it is an honor for me to give a talk at IAST where both my teacher and student are faculty. So it's good. See, today I will be talking on climate variability, predictability, and prediction. So not only the decadal, though the title says decadal. The outline of my talk is touch upon the inter-annual variability in the Indo-Pacific region, then the decadal modes of variability in the Pacific and the teleconnections, decadal variability of the Indian Ocean and the Atlantic Ocean, and predictability, and some prediction efforts, decadal prediction efforts of CLIVAR and the CIMIP team and India, and some of the science questions and challenges the decadal prediction teams face, which may be useful for the students. So this is a very familiar, anybody gives a talk on monsoon variability or climate variability, they'll first show you this. This is the intra-annual rainfall variability, Indian summer monsoon rainfall variability. So what you see, the red lines are the negative anomalies which are exceeding 10% of standard deviation. Similarly, what you see blue, they are 10% above normal. So these are above normal, these are below normal. You can also see some circles. The red circles represent El Nino years and the blue circles represent La Nina years. So it is seen that most of the deficit years are the years crossing minus 10%. So they are associated with El Nino years, you can see. And most of the years exceeding the plus 10%. So you can see most of them are the La Nina years. But you can also see many years, like you can see here 94, the excess year. But that is not a La Nina year. And similarly, you can see years in the deficit which are not El Nino years. So, for example, 2014 was a recent years, which was not a El Nino year, though it was evolving as type of El Nino, but it was not an El Nino year. But you can see that that's a deficit year. I mean, if you look at the comparison, here in this scatter diagram, the x-axis is the Nino 3 SST anomaly standardized, and y-axis is Indian summer monsoon rainfall anomaly. So what you can see is there is a close relationship. So they are all scattered along a line. So this slope indicates that when there is El Nino, the positive phase of Enso, the rainfall is negative. So you can see, but there are years which are not following this. So that is why you can see some scatter also. Now, if you look at the Pacific SST evolution, so this is normally seen using the EOF analysis or empirical orthogonal functional analysis. So this is the first mode of EOF. You can see these are nothing but the eigenvectors, the first leading eigenvector. So you can see that they resemble the SST anomalies associated with the El Nino. And that is seen in the principal component. See here, there are two lines here. One is black. The black line is the principal component associated with this pattern. And the red one is Nino 3 index. So which is the SST anomalies over the Eastern Pacific. So you can see they correspond very well. So that suggests that the sea surface temperature or the warming pattern we see associated with the El Nino actually represents the leading mode of variability in the Pacific, tropical Pacific. But if you look at the second mode of variability in the sea surface temperature, you see slightly different pattern with warming over the central region rather than central to Eastern Pacific. You can see warming over the central Pacific and cooling. See opposite. This EOF sign doesn't represent that it is only warming. This is contributed by both warming and cooling. For example, here, this representation is contributed by both warming due to El Nino and cooling due to La Nina. Similarly here. So what you can see is there is an opposite relation. So when the Central Pacific warms, the East Pacific cools. So when Central Pacific cools, the East Pacific warms. So if you look at the principal component, the time evolution of that variability, you can see that is resembling the trans-Nino index. Trans-Nino index is the difference between the Nino 4 or the Central Pacific based Nino index and the Nino 1+2. So that is along the coast. So the leading modes of variability actually explains two types of El Ninos. So one is, you can say, East Pacific or the canonical El Nino. This is the Central Pacific, or people now call it Modoki. Some people call it Modoki. It is Central Pacific El Nino. So for a typical El Nino, so this picture very clearly portrays the Pacific conditions during normal period. So you have intensified trade winds here. Trade winds push warm surface waters to the western Pacific, making the West Pacific warm. That is also reflected in the thermocline. You have a deeper thermocline in the West Pacific, and because of the easterlies here, you have large upwelling over the eastern Pacific, and that will show the thermocline in the East Pacific. So you clearly see a thermocline tilt with deeper thermocline about 200 meter in the West Pacific and very shallow thermocline in the order of 50 to 100 meter in the East Pacific. Now, if you look at the conditions during El Nino years, you see the warm waters coming to the Eastern Pacific. So now the entire Pacific is warm. If you look at the surface conditions, the entire Pacific is warm. And if you look at the thermocline, you can very clearly notice the tilt in the normal conditions is absent during the El Nino condition. So the tilt is weakened. Now the thermocline in the west and east are almost at the same depth. And this is during the La Nina conditions. If you look at the La Nina conditions, the thermocline gradient or the thermocline tilt intensifies. And if you look at this is another picture where you can see you can visualize the three-dimensional structure of Monsoon, El Nino, for example. So if you look at the top plane, the surface, you can see there is warming from East Pacific to Central Pacific. But if you look at the subsurface, so this is up to 300 meter, maybe at a depth of 150 meter, 100 to 150 meter, what you can see is it's a much stronger warming compared to the surface warming. The surface you can see 2 to 4 degrees centigrade warming, but what you see here, the subsurface is about 8 to 10 degrees centigrade warm. So similar thing you can see in the Western Pacific in the opposite sign. So this is during a typical peak phase or the matured phase of an El Nino. You can also see that in the sea level. So you can see the positive sign representing the downwelling phase of your wave and negative representing the upwelling phase. So there are positive sea level in the east and negative sea level in the Western Pacific. And actually, if you want to stop me in between, please stop me. Okay, so instead of reserving all the questions to the end, so you can interrupt me and ask questions if you want. Okay. So now this is the El Nino indices, like, to identify and classify the different types of El Ninos. So there are weak El Ninos, moderate El Ninos, strong El Ninos, and very strong El Ninos. So recently there were 3 very major El Ninos. So one is 82, 83, 97, 98, and the recent event 2015-16. And this clearly says when it peaked. So like the 82-83 event peaked in January 83. The 97-98 event peaked in November 97. Similarly, the 2015-16 event peaked in December 15. You could see that the evolution of SSTs in the global ocean associated with that. Now, if you look at the sea level pattern associated with the 2 types of El Ninos. So one is the East Pacific El Nino, or the canonical or traditional El Ninos. So what you can notice is the sea level pressure anomalies. You can see right from tropics to even mid latitudes and higher latitudes. See, and similarly the opposite in the west, that also has large extension. And the Pacific, especially in the Pacific, you can see it is not only confined to the tropics. And if you look at the Central Pacific event, the second type of El Nino, you can see a typical different pattern with opposite polarity with the North Pacific and the North American region. And if you look at the SST pattern associated with the East Pacific event, you can see the signals, the relationship with even the Indian Ocean. You can see it suggests that when you have El Nino in the Pacific, your Indian Ocean SST also warms. So when your SST in the East Pacific warms, SST in the Indian Ocean also increases. So that is a pattern you can see very closely for the Eastern Pacific event. And if you look at the Central Pacific event, you still see warming over the Indian Ocean, but the intensity has reduced. So it is much weaker compared to the East Pacific El Nino induced warming. If you look at this is the typical SST evolution associated with El Nino. Okay, so this is the case for 97, 98. You can see in the y-axis time from 96 to 98 are plotted here. You can see the warming started sometime. You can see that the red and yellow, this is the warming. So the scales are here. You can see from March, April 97 onwards, you can see there is warming in the East Pacific. If you look at the pattern, see the warming first, see, you can see this warming first starts in the East Pacific, maybe in May, June, but then it slowly propagates to the West Pacific. So that is the sort of SST anomaly evolution associated with a typical El Nino. And when you see here, the D20 or the thermocline depth, if you look at the thermocline depth, so you see there are some propagation of the thermocline signals from West Pacific to the East Pacific or Central Pacific to the East Pacific. So you can see right from the 96 December. So there are events. And these warming and the thermocline events are these are we call waves, or the Kelvin waves, because we are looking at the equator. So these waves are closely associated with what you see the warming over this way. So now, if you look at these the wave pattern, the Kelvin waves, if you look at the forcing, these are the zonal wind. You can see the winds, right? These are westerly bursts. See the color shades, red ones are westerly bursts, westerly winds. You can see the westerly bursts from December, February, March, April. See there are sequence of westerly bursts right from December to December 96 to December 97. So you can see several westerly bursts. So the hypothesis can be derived from that these westerly bursts. So once you have westerly winds along the equator, there will be convergence of water mass along the equator due to Ekman flow, that they create downwelling, and these downwelling will then propagate eastward as downwelling Kelvin waves. And when these downwelling Kelvin waves reach the East Pacific, they push the shallow thermocline in the East Pacific down and allowing the East Pacific to warm. because in the normal conditions you have very shallow thermocline here. Shallow thermocline means the cold water is available at a shallow depth, so that is not favorable for warm. But once you push the thermocline down, the East Pacific starts warm. So that is essentially responsible for this type of warming pattern in the East Pacific. You can see in this figures also. This is the picture in 97 January. So you could see, you remember in December 96, we have seen the westerly burst. So they triggered deepening of thermocline. You can see that this is by April. This is January picture, January 97. In January 97, actually you don't have any signals in the East Pacific. In fact, East Pacific was cold. But there are strong warming up to 4 to 5 degrees centigrade warming in the subsurface, in the thermocline level in the West and Central Pacific. So now if you want to really forecast the El Nino, you can actually do it about a year back, because there are signals in the subsurface. So if you have observations over this region in the subsurface, you can actually predict the next El Nino about a year ahead. So this is the picture of April. So by April, these Kelvin waves are the waves reach the East Pacific now. So you can see the warming up to the East Pacific, though the signs are not clear in the surface. Surface you don't see much in April 97. But if you see in September, so you can see it's large warming you can see. But in September, if you see, there is another cooling event is also, there's a cooling here. This is the picture in 98 January, 98, it's in 98, it's in the peak phase, but then there's a cooling coming from the Western Pacific again. So that is going to kill this warming. So this is a picture of 98 March. So almost the El Nino conditions in the surface has weakened. And this is the May 98. So it's almost El Nino is gone. And this is the, this is an animation of 2014-16 event. So if you see here, 14, there are Kelvin waves. So all the operational agencies forecasted 2014 as an El Nino year, but it turned out to be a neutral year. So you can see the next, after 2016 it is going to come in 2014. You can see 2014 there are large downwelling Kelvin waves, but then essentially see here, see 2014, but it did not form as a, so that science question is, say, whether all these Kelvin waves lead to El Nino or not. So 2014 is a typical case. Unless you have air-sea interaction associated with this to support this event, you don't get proper El Nino evolved. So now El Nino, there are many theories for El Nino. If you see here, see the blue line here is the Nino 3 SST, Nino 3 SST and Nino, the El Nino index. See. But the red line is the warm water volume. So this is integration of the thermocline depth over the equatorial Pacific. So what you see is before the ENSO, before the El Nino events, before all the El Nino events, or before the Nino 3 SST peaks, your warm water volume peaks. So you can see before all the events. See, 27. So this strongly suggests that there is a close association between the El Nino formation and the warm water availability in the tropical Pacific. Now, if you look at the vertical structure of Pacific, so this is what you see prior to an El Nino. And this is what you see during an El Nino. And this is what you see after El Nino. So this clearly suggests that you need to recharge the Pacific, especially the West Pacific, because that is the region where the thermocline is deep. So you first recharge the Pacific, and then the El Nino is a process to discharge this heating, and this is like a discharge phase, or a La Nina phase. So people see this El Nino as a recharge-discharge process also. So you can see, El Nino is very important because it has impact on everywhere. So you can see the impact over the globe. So these are the circulation changes, because during El Nino time, you have more warming in the Central Pacific and East Pacific. So the conventional, the convection over the Western Pacific in the normal conditions, because the West Pacific is warmer than the Eastern Pacific. So the convection over the Western Pacific during El Nino years get shifted to the Central Pacific. So literally your Walker circulation. So this is the Walker circulation. You can see convection over here and subsidence over the Eastern Pacific region. So this Walker circulation get reversed with circulation, with the convection over the Central Pacific and subsidence over the Western Pacific and the Indian region. So that is why these El Nino have strong impact on Indian monsoon and the Indian Ocean. So here you can see very clearly. So this is the Nino, the NDJ, that is the time November, December, January, Nino 3, correlation with the global SST. What you can see is when the Pacific warms, so Indian Ocean also warms. So that you can see whether Nino 3 or Nino 3.4, let's say. So if you look at how this warming evolves, like, the dashed line here is the evolution of El Nino. You can see with the time. You can see it peaks during November, December, January, and then it decays from April or May. But if you look at the Indian Ocean SST, what Indian Ocean SST warming, you can see it start warming when ENSO is at a peak phase, and this warming continues. This warming continues even after El Nino decays. So this means that Indian Ocean is going to remain warm during the next monsoon season. So the impact of ENSO on monsoon is not only limited to 1 year, it is limited to more than 1 year, at least 2 years, which can be very clearly seen here. See, during a typical ENSO case, when there's warming over the equatorial Pacific, as the gill response, you get anomalous cyclonic circulation developed in the west of your convection, west of your warming, and this cyclonic circulation will intensify the trades here. See, because already the winds are northeasterlies here, and these cyclonic circulation will intensify the winds, so they cool the ocean here. So when ocean cools, there will anomalous anticyclonic circulation develops here, and there will be an anticyclonic circulation west of it, and this anticyclonic circulation, which is now against the anticyclonic circulation, is against the trades. So this region gets warmed up. So there will be warming over here. So the changes what you make over the East or Central Pacific, so they have chain impacts over different regions. So now this is the case during December to February. Now if you look at the next season, these anticyclones, like what you see here, this anticyclone gets pushed to the western region, even up to the Bay of Bengal region, and with these anticyclonic winds, you can also see there is a Rossby wave generation associated with this wind response. You can see there is a Rossby wave here, and these Rossby waves will move. It's the mechanisms I'll explain later. So these Rossby waves, oceanic Rossby waves, they propagate westward and warm the western region and central Indian region. So you have warming over here, you have an anticyclone over here, and that is going to create a wind, symmetric wind, with northeasterlies here and northwesterly here. So now this is the case. This is the case in June, July, August. So you have an anticyclonic wind here. The June, July, August, the warm Indian Ocean remains. So now you have these anticyclones feed the Indian Ocean, and it is opposite to the monsoon winds. So that is favorable for Indian Ocean warming, and this warming now will induce northeasterlies that will amplify the anticyclonic circulation. So in a way, there is a strong air-sea interaction associated with the response what we see to ends. So it's a very non-linear, complicated interaction between the Pacific and the Indian Ocean. So now, when you look at these features, the ENSO that may be up to March, but the Indian Ocean warming, which persists for the next summer, in close association with the Northwest Pacific circulations. So it is important to note that the Northwest Pacific changes induced by the Eastern Pacific warming has important role in sustaining this warming over this region. It's also like if you see this during El Nino in the Indian Ocean, you can see the wind pattern. If you see, there will be subsidence over the Indian Ocean and the eastern and in the Western Pacific. So that will induce easterly winds here. So these easterly winds actually support downwelling over this region, and they will actually amplify the Rossby waves generated from the east. So these Rossby waves, what we see here, is actually a forced Rossby wave because it is forced by the wind responded to El Nino. So it's a very nice air-sea interaction. In fact, it is both the thermocline SST interaction and the SST atmosphere interaction. So it's a very complicated air-sea interaction process. And this actually turns out to be the warming, what you see, the basin-wide warming. This turns out to be the leading mode of variability in the Indian Ocean, SST. So it explains about 40% of the variability, interannual variability in the Indian Ocean. And what the interannual variability called IOD, Indian Ocean Dipole, what we know, he is explaining only 12% of the variability. But they're important because the impact of them on monsoon is important. It's significant. So during a positive IOD, so you have cooling over here in the eastern equatorial Indian Ocean and warming over the western equatorial Indian Ocean with more convection over west and subsidence over here, and opposite But during this time, when a positive phase of a IOD, you can also see clouds over the central India and Indian region. So that is why the IOD, though it is explaining only 12% of the variability, but they are important because they support the positive phase of a IOD supports rainfall over the central India. Central India is a region where we get more rainfall. And similar, the thermocline dynamics is associated with the Indian Ocean also. So this is actually mainly due to the Bjerknes feedback, so which is very clearly seen in the Indian Ocean also. Now, if you compare the normalized ISMR, that is the Indian summer monsoon rainfall, that is the bars, with Nino 3, that is the red one, and IOD index, that is the green one. So you can see the close relationship between them. Especially you can see the years like 94. 94, when you have the IOD, see how the monsoon rainfall became above normal. And also you can see in 97, there is El Nino, the red is El Nino, there is a strong El Nino, because there was an IOD, so the effect of El Nino on monsoon was not seen. So you have above normal rainfall in 97. You can also see the relationship between the ENSO and IOD on the spatial variability or spatial relationship. You can see El Nino can actually decrease rainfall over the entire India, and the IOD can increase increase rainfall over the central Indian region. So this explains the month-wise, like which month is contributing to JJS rainfall. The July IOD contribution on rainfall is mostly over the central western region, and August IOD is mostly contributing to the entire central Indian rainfall. So by looking at the IOD index, so you can actually if you can predict El Nino and IOD, you can get very good information or forecast information about the rainfall over Indian region, especially the central Indian region. But now, if you look at the models, see, because if you want to forecast, you have to see the skill of models. So here, this is the standard deviation in the dipole mode index from different models. So these are the models. There are many models here, and the black one is the black line is observation. So what you see is the observed standard deviation or the variation. So that is about 0.4 degrees centigrade. But if you look at the models, most of the models, they over predict the IOD. The amplitudes, some of the models, the amplitude goes to 1.5, where the actual variability is at 0.4. Actual standard deviation is 0.4. So that is a serious issue, because the model may have tendency to give you wrong information about the IOD, so that it has it actually loses the prediction value. You can see here, so there are many models. Suppose if you take ensemble mean of all these models, so they come out to be like this. So observation is at 0.4, but even if you take mean of all the models, they are about 0.8. So that actually affects the prediction value. Now, if you look at the Pacific and Indian Ocean very closely, the processes, so I'm sure most of you are aware of this, but for the sake of the first year students, so I thought I will simply, I'll very simple way, I'll explain what mechanisms are associated with the El Nino and IOD. So now we have seen in the case of El Nino where there are westerly bursts, so westerly winds. So these westerly winds, if you look at the Ekman flow, these in the northern hemisphere they will be right of your wind, so they will be towards equator. In the southern hemisphere they will be left of your wind, so they will be towards equator again. So both from north and south, the Ekman flow will be towards equator. So that will converge water mass here. They will push the thermocline down, so there will be downwelling, and these downwelling waves propagate eastward and warm the eastern basin. Now if you look at the wind pattern, see, along the equator you get maximum winds, and off equator you get weaker winds. So these are going to create cyclonic shear. So these cyclonic shear, both in the northern hemisphere and southern hemisphere, these cyclonic shear will induce upwelling, because cyclonic wind stress curl can induce upwelling. So they induce upwelling, and these upwelling will shallow the thermocline. These shallow thermocline, they propagate westward as upwelling Rossby waves. So that is the dynamics here. So just the opposite happens here, because here the anomalies are easterlies. In the Pacific you have westerlies, in the Indian Ocean they are easterlies. So the process reverse, you will get upwelling Kelvin waves and downwelling Rossby waves. That's the difference. So here this process is very closely associated with the air-sea interaction, and that's a Bjerknes feedback. So Bjerknes feedback is a feedback between the atmosphere and the ocean. So here, when you say you start from one, so El Nino is an ideal case for a positive Bjerknes feedback. You have a warm, you start with the warming over here. You warm this region, the pressure falls here. So there will be westerly winds. These westerly winds will deepen the thermocline. The deeper thermocline, they propagate eastward as downwelling Kelvin wave, and they favor warming over the region again. So you start from warming, you end up getting warm. So that is the positive feedback of Bjerknes. So that is what is happening during the El Nino or La Nina. During the La Nina, the opposite, but again the positive feedback. Now with this interannual variability, let us now move to low frequency modes of variability, or the decadal or multi-decadal variability. Now, so this I just took the East Pacific or the canonical Pacific and the Central Pacific events and associated sea level pressure pattern and sea surface temperature pattern here. But this is in the interannual time scale. Okay, now if you look at the decadal time scale, low frequency modes, this sea level anomaly, so this is associated with Aleutian low. So what you see is there's the low pressure over this North Pacific and a high pressure over the Western Pacific. And you can also see the North Pacific oscillation. This is the Aleutian low pattern. See, this is the North Pacific oscillation pattern. So you have a high pressure over the north and the low pressure over south, showing a north-south oscillation pattern. So this turns out to be the first and second leading modes of decadal variability in sea level pressure. So the sea level pressure, what you see here, is the first mode of EOF, and sea level pressure pattern, sea level pressure anomaly pattern, what you see here is the second mode of variability. Now, if you see the ocean response, this is the atmospheric pattern, sea level pressure pattern. But if you look at the corresponding ocean pattern, the sea surface temperature pattern, you get a pattern. This is called the Pacific Decadal Oscillation. So you have warming in the east and the cooling in the west central Pacific. A pattern you can see, you often get confused with the El Nino pattern. So if you see, there are some differences between these two patterns, but there are a lot of similarities. If you see both sea level pressure pattern, the Aleutian low pattern, and the pressure pattern associated with the East Pacific El Nino, there are similarities. The sea surface temperature pattern here and the Pacific Decadal Oscillation pattern. So there are similarities. Similarly, for the North Pacific Oscillation, the second mode of variability, the SST pattern, if you look at, so you get something what you see here during a Central Pacific event. So this suggests that the decadal modes of variability in the Pacific and the interannual. So interannual means they vary from year to year, and the periodicity is 4 to 7 years for El Nino. But the decadal variability, they are decadal and multidecadal. So you will see the signals from 16 to 30 years periodicity. So, but the important point to note is they both have similar patterns of SST and SLP. So there could be strong connections and strong relationship between all these modes of variability. Now, I'll just introduce the Atlantic multidecadal variability. In a multidecadal sense, you have the North Pacific warming and cooling. So, in few decades, the North Atlantic warms, and in few decades they cool. They are closely associated with the meridional overturning circulations in the ocean, in the Atlantic. So that's called Atlantic meridional overturning circulation. That's a very important phenomenon, especially for the climate change perspective. Now, when the AMOC, Atlantic meridional overturning circulation, AMOC, when it weakens, you get warming over here, and when it strengthens, so you have cooling over here. So this the warming and cooling has strong connection with the Atlantic meridional overturning circulation. Now, similarly, this is a PDO, the Pacific Decadal variability. If you see, the PDO signals what we have seen in the previous slide. So you are warming over here, and if you look at the equatorial region, it resembles the El Nino pattern. But in the North Pacific, they have the Pacific Decadal variability pattern. But people see that if you see the entire Pacific as a whole, what you see in the North Pacific, you see in the South also. So there are some cooling here and resembling, not exactly like a North Pacific, but there is. So they call it interdecadal Pacific variability or Pacific oscillation or IPO. So if you combine the entire Pacific, these signals are correspond to the interdecadal Pacific oscillation. So essentially, both the Pacific Decadal Oscillation and in interdecadal Pacific Oscillation, the patterns are same. And you can see the signals, the PDO, Pacific Decadal variability, has strong imprints on the Indian Ocean. Okay, so here, this is like for a warm phase of PDO and cold phase of PDO, how the Indian Ocean responds. Now, if you look at, see here, we regressed the AMO index. AMO index is just the SST anomalies over the North Atlantic. That AMO index, if you regress with the sea level pressure and precipitation, you get a pattern here. What we see here, the shaded ones are sea level pressure regressed on AMO, and the contours are precipitation, rainfall regressed on AMO. So what you see is that there's a large pressure drop over the Indian region associated with the AMO, and there is a strong positive rainfall over the Indian region associated with the positive AMO. So AMO positive phase is favorable for good monsoon over Indian region. And if you look at the similar regression with the PDO index, you can see the opposite pressure pattern here with the positive sea level pressure anomalies over the Indian region and suppressing the rainfall over this region. So positive phase of a PDO, you get negative rainfall anomalies and a positive pressure anomalies, and positive phase of a AMO, you get negative pressure anomalies and a positive precipitation, positive rainfall anomalies. So AMO positive phase favors monsoon, and PDO positive phase is opposed. It's weaken the monsoon, and the negative phases are the opposite. So this is what I was talking about. If you look at the PDO index and the ENSO index, you can see there are close correspondence, close association between them. So it strongly suggests that there is strong interaction between the tropics and higher latitudes. And if you see, for example, the frequency spectrum, power spectrum, if you see the power spectrum, you can see here the thick line, thick color black one is ENSO, and the lighter one is PDO. See, what you can see very clearly, there are signals. For example, in the 7-year cycle, the cycle is here, so here, and the frequency here. You can see in 7-year cycle, you have both PDO also and ENSO also. Similarly, in the lower frequency, at 30 to 50 years, so you can see there is a PDO is strong, but ENSO is also having a peak. Similarly, here in the interannual time scale, a 7-year period, 5 to 7 year period, you can see the ENSO is dominating, but the PDO is also having a peak. That's why I was telling you that these two modes, the PDO and ENSO, have strong interaction and feedback. So this is just to show that the models can be, a simple ocean model can very easily, very clearly simulate the PDO signals closer to the observables. So this is an ocean model simulations, and even the index here. So this is how the mid-latitude tropic interaction takes place. See, like the Pacific decadal oscillations. See, the PDO has a very close relation because they generate the ocean waves. These ocean waves, ocean Rossby waves, they have signals and they amplify the teleconnections when they propagate westward towards the Western Pacific. So these changes, what you see associated with the PDO, they have a close relationship with other modes of variability in the Pacific. For example, the PDO and the Kuroshio-Oyashio extension and the Aleutian low, they all feedback each other. Similarly, the PDO, ENSO, then ENSO to the atmospheric bridge, it again feedback the Kuroshio-Oyashio extension. And so all these modes of variability they feedback each other and make a multi-decadal or a decadal variability. Similarly, the North Pacific Oscillation, what we have seen in the pressure oscillation between North and the mid-latitude Pacific, you can see they have a strong effect on the North Pacific gyres oscillation. And that again has a feedback on the Central Pacific warming, and again they have the feedback on the Kuroshio-Oyashio extension, and again it feedback to the North Pacific Oscillation. And see, in a way, all these modes of, so you can see here in the Pacific, there are many modes of variability, and all these modes have interconnection and the feedback. And you can also see this, because this is the modes and the sea level variability. See, there are tide gauge observations available over 100 years at some stations like Mumbai, for example. So the black line here is the sea level, the tide gauge observed sea level. That's a black line, and the one you are seeing, the multi-decadal variability, that's a smooth one. If you take some running mean, you will see a decadal signal in that. So, and if you see the AMO index, that is the red one, the AMO index and the sea level over Mumbai, they are closely correspondent, and with a correlation coefficient of 0.37. So this suggests that the AMO can actually induce sea level rise over the western coast of India. For example, the West Coast Station, Mumbai. Similarly, you can see the PDO index. If you see, so they have opposites. See, during a positive phase of PDO, so you get the sea level low. So, or the PDO can actually, positive phase of a PDO will reduce the sea level over the Mumbai region during, see, it's an opposite relationship, but what we saw mainly due to the pressure pattern, that we saw the similar picture in the pressure changes also. So here, the AMO reduces the pressure, whereas PDO increases the surface sea level pressure. Okay. So now, so I don't know whether I'm going in the right way. So if everybody is following, or can I go ahead? Shantini?
Yes, sir.
Can I continue, or is there any time limit?
No, it's okay. You can continue, maybe.
You please tell me, because I have many slides. You tell me, you maybe 5 minutes before, you please stop, give me some message that.
So the scheduled lecture was for an hour, but you can continue maybe a little bit more. Because
I mean, I can continue because I have a lot of materials.
okay.
See, students, we can ask, because I think 1 hour I have taken, the scheduled talk is over. Now we will ask the student whether I can continue, or they want to spend more time on interaction, because
Okay.
a lot of slides. So because the prediction, I have some slides on the. So what they want to hear this talk for another maybe half an hour or so, or they want to spend some time on interaction and maybe discussing on some fundamentals and like that. I mean, it is up to them. I can.
Okay. So I will ask all the students who want to speak up. Please speak up now. If you have questions, you may have a lot of questions to ask. If you don't understand any part, you can ask. Professor Chandrasekhar, you want to say something?
Yeah, good afternoon. I'm sorry I just joined a little late.
Yeah, good afternoon,
but
sir.
Yeah, it was very interesting talk. Of course, I have a lot of, I don't know much about many of the aspects, because only thing, some couple of some small clarifications I just wanted to know. Now, I have heard that this relationship between the El Nino, the ENSO, and the Indian monsoon sort of strengthens and weakens every about 20 years. Is that right?
Yes, but see
And
now, yeah, there are some periods when the relationship weakened.
yeah.
Now again it is strengthened. Yeah, that is
So,
true.
so is that weakening attributed to the dipole mode always or no?
It is not always. So it is also related with the phases of PDO. It is also related with the response of Indian Ocean to this forcing. Because the Indian Ocean, because that is what I mean. The next slides are actually leading to such problems. Because maybe I will cover 2-3 more slides where
Okay, fine. So
even
another question I had was with this dipole mode. Now the positive index of the dipole mode provides where you have the western part is warmer than normal and the eastern part is cooler, right?
right.
Yeah. So how long does it last? The
Yeah, because see here in the Indian Ocean there are seasonally reversing winds, so you can't, and the basin is very small, so the warming or cooling, especially the eastern region, what happens, that cannot last for more than a season or two. So the IOD as such cannot sustain for more than 2 seasons. Whereas the basin-wide signal, see, that can last, but a dipole pattern cannot last for more than 1 to 2
Now,
seasons.
when we say El Nino, like we say that it has got a time scale of about 2 to 7 years, right? Do we have a similar
Right.
time scale for IOD? And what is that?
See, that is what I was explaining about. Oh yeah. See, first I will answer the question. See, here in the Pacific, you have
Larger basin.
ENSO has a 2 to 7 year
Yeah.
cycle. Say in the IOD, you have 1 to 2 years, like 1 year. It's like a
Okay.
annual. Mainly because I was sometime back I explained the wave mechanisms. The, the Westerly burst and the Kelvin waves and the Rossby wave. See, you were there during that discussion?
No. I think I missed that one.
Yeah, that
Okay,
is.
one more quick question is you showed that the correlation of the dipole mode actually provides positive correlation over central parts and northwestern parts, right? Over
Right,
India
right,
during
right,
June, July, August. Uh,
right. July, August, yeah.
September, July, August, September.
Yeah,
So
right.
maximum is sometime around July,
July,
August, right? Yeah.
August, yeah.
No, but I have heard also that there is also correlation with the northeast monsoon. Am I correct? The
Yeah,
October and November. That is much more stronger than the
yeah,
south.
yeah. The correlation with the northeast monsoon is much stronger.
Yeah. So I saw your figure was restricted only to September. So I was
Yeah,
just
yeah,
curious to know.
because see, we normally, when we talk about monsoon, we are mostly, we are biased towards southwest monsoon. That is the large part of.
So does it mean that this dipole mode can actually provide a practical utility in forecasting the northeast monsoon more than the southwest monsoon?
Yeah, southwest monsoon, because see, southwest monsoon and the IOD evolve almost simultaneously, so the prediction value is less. Whereas for northeast monsoon, it can give the prediction value is more, because you can predict at least a season before. Yeah. I'll answer to your
So
question.
this when you have this warming over Central Pacific or over Eastern Pacific, you showed that you have concomitant, parallel, simultaneous warming over the Indian Ocean also, right?
Right.
Of a smaller magnitude. Now,
Right.
is this attributed to the downwelling motion of the resultant Walker circulation shift?
Exactly. Yeah. That is. See, there are two things. There are atmospheric pathways and the oceanic pathways.
Okay.
The atmospheric pathways is what you just mentioned. That the substance
So
of.
does it this is
Yeah.
Atlantic also? No,
Yeah,
does the
yeah.
warming
That
over
you can see. So
Pacific
now
affect
that is.
Atlantic also?
Yeah. it affects the subsidence over the Atlantic also. See, yes, in that Atlantic, tropical Atlantic also change. Yeah, so that is mainly due to the subsidence.
Okay.
Subsidence and due to subsidence, there will be more clear sky and the radiation will be more. And
but this subsidence we also have, right? Somewhat during the, I mean we have this reverse Hadley circulation.
yeah,
You
yeah.
have ascending motion over around 30° north, and you have descending motion over the equatorial region.
Correct.
So
Yeah.
this actually increases the subsidence, or because
Yeah,
normal course also you have
because
subsidence, right?
see, during El Nino, the subsidence, even the reverse Hadley also will weaken, because the subsidence what we see is not only confined to the equatorial region. It has a wider the latitudinal structure, so you will see the subsidence over the Indian region also. And
to what latitude?
say up to maybe 15-20 degree north also you will see the subsidence.
Okay. But Walker circulation is essentially
it's a major. See, you see the dominant signals along the equator, but the subsidence, when you see, you will see over. It's not only confined to the equator.
One final question. So one final question. Suppose do we? So we have this situation like you have an El Nino. It reaches its peak intensity and then sort of weakens. Now you can either lead to a normal situation or it can go to a La Nina situation. Correct?
Right.
So
or it can go to El Nino also. See, it can again go to El Nino.
Okay, but it cannot go to El Nino without going through the normal, right?
See, sometimes there are called the persistent El Ninos. So there are years when the one El Nino.
So that means you can have an El Nino which lasts for 3 years. You mean to say?
Yeah. That is why that cycle becomes the 4 to 7 years. See, it can persist. Yeah. Because, for example, see, you can say even the 2014-15, the 14 actually was El Nino, though our indices doesn't say that. There were 2014, if you see, 14 summer months, the El Nino conditions were persistent. But then, due to some easterly burst, see, the whole thing, I mean, that is still not understood how the easterly burst took place. So the entire thing it got disturbed. The El Nino did not develop into a peak phase, but it was, if you look at the oceanic conditions, as I said, the El Nino discharges the heat, that the discharge was not taken place during 2014. So the 2015 El Nino had to take place, so that the entire till the entire heat is discharged, the warm conditions will remain. So the El Nino is basically removing the heat deposited in the equatorial Pacific. Yeah, so it can actually go for the next year, but in most of the cases it decays by summer, by next summer or spring.
Okay, thank you.
And their impact on monsoon will be totally different also, because the impact of
coming to the central equatorial Pacific El Nino and the eastern equatorial Pacific El Nino, this central equatorial is possibly more recently formed, right? Maybe 20 years.
In the recent years, most of the events are central Pacific.
Equatorial.
Yeah, right.
So which is the most what I should say most damaging for India?
More damaging. See, it's like
the rainfall, bad monsoon.
Yeah. See, it's like the canonical or eastern Pacific El Ninos are having more impact. But the central Pacific El Ninos also have the negative impact. So if you see, both are almost same. But on the oceanic part, like Indian Ocean part, the Eastern Pacific is shown to be more, impact compared to the Central Pacific. But as far as rainfall is concerned, both can, because see the convection over the Central Pacific, see even during the Eastern Pacific or the traditional conventional El Nino, the Walker circulation reversal is mainly due to the convection over the Central Pacific, not mainly over the Eastern Pacific. So mostly because the Central Pacific is warm enough so that any excess warming will accelerate convection over the Central Pacific.
Okay, thank you.
Yeah, I will actually, if you are still interested in the question where the Pacific it will be 4 to 7 years, whereas Indian Ocean it is like 1 year. Why? Because in the Pacific these waves, because the mechanism is like this. You have the westerly burst, then it creates the downwelling Kelvin waves. They need to propagate and reach the Eastern Pacific. So they take 2 to 3 months here. Now,
so westerly burst associated with El Nino.
That is a question which is not.
Because this is like reduction of trade wind, right? Is that what you mean, westerly burst?
Yeah. There are, if the westerly burst, during the westerly burst, the trade winds will weaken. Right. Yeah. So now, because this is like due to that. See, now, according to Bjerknes positive feedback theory, so this warming will never disappear. This warming will continue forever because of the air-sea interaction associated with this and the Bjerknes feedback. But now the problem here is with these westerly bursts, with the downwelling Kelvin waves, there will be a pair of upwelling Rossby waves generated in the off-equatorial region. These Rossby waves, they propagate and reach the west coast, and then once they reach here, see always these waves have a property that in the northern hemisphere they keep land right of the waves. So they cannot keep the land in the left and move. So in the northern hemisphere they keep the land in the right. So when they reach here, they can only propagate towards the equator. Similarly, in the southern hemisphere, the waves, when they reach the west, the Rossby waves, they are upwelling. When they reach the west coast, they keep land in the left side. And so again, they propagate towards the equator. So both these Rossby waves, after reaching the western boundary, they come towards the equator as upwelling waves. So these upwelling waves, after reaching the equator, they propagate eastward as upwelling Kelvin waves. So now the whole thing, because the Rossby waves travels at 1/3 of the speed of Kelvin waves, and these they have to move. They're slow. They take some time. Then they reflect, and again they come as the upwelling waves and the sort of kill the body. So the entire process takes, because the Pacific basin is a very big basin, so it takes more time.
So that is
whereas in the Indian Ocean, that is in the Indian Ocean. See, the Kelvin waves won't even take 1 month to cross the basin.
Okay.
And even if the Rossby waves take 3-4 months, so you have, within 2-3 seasons, the effect will be cancelled by the downwelling waves. So that is why in the Pacific, the El Nino ENSO variability is 4 to 7 years.
Okay. Thank you.
Yeah. No, actually, So actually, I took only up to the basics, but now I have more research stuff. So I don't know, because I don't want to. Because basically, I planned that first, but then I know it is for students. That is why I took more of fundamental things. If somebody is really interested in more research stuff, I can take. But better, I will take more questions. See, if students ask some questions, I will be very happy.
Yeah, so it's
one point, because it is relevant to what you asked also. So if you see here, there are a lot of changes happening. See this picture. See this one is the decadal UIF, first decadal UIF of Indian Ocean SST, and this is the decadal UIF of Pacific. So this we call PDO or IPO or something like that. And here, this is the Indian Ocean basin mode we call. So because it's very important because it explains 58% of the variability. Now, if you look at the PC, the black one is the Indian Ocean basin mode, and the red is IPU or PDU. So what you can see is there is a phase correspondence between the Pacific and Indian Ocean till maybe 1980s. But after that, especially in the recent years, this phase has changed. So there is a lot of change. Because of that, the relationship between different modes have changed. Even the association between them and the monsoon has changed. So that is why from 90s, even the AMO index and monsoon are not related. So the whole thing is, the relationships underwent drastic changes from the 90s. So that is a problem here, very important research problem. Need to be.
These are all from observations, right?
Yeah, these are all from observations, yes. Yeah, these are from observations.
Obviously, no coupled model can simulate it, even close to this. Or can they simulate?
Coupled model cannot simulate well on all these things, because see, there is a lot of changes in the basic state of the ocean. The coupled model, most of the coupled models have problems in getting the thermal structure of Indian Ocean or the mean state of the Indian Ocean. That is a problem. So that is why the coupled models have problem in getting this type of signals. They can overall get the relationship. What you see prior to 80s, they can reproduce, but what you see here in 90s, so that the models, the current models cannot. Yeah.
So one last question. This dipole mode over Indian Ocean, you said, although it's a very important thing, this thing, variability associated with the Indian Ocean. You say it explains only 16%, right? It is only
12%. 12%. Yeah.
So why is that? I mean, then the most dominant variability should be able to explain better, or?
Yeah, around 40%. See, around 40% is explained by.
Any reason why the dipole is so low? 12%? No.
See, it is not because of that. The ENSO, ENSO is what happens is ENSO signals in the. Oh, okay. I'll explain you why that percentage is. Why the variability, the second mode is low. Actually, the
second mode always has to be low compared with the first mode. That is
it is lower than the first one.
It is much lower, right?
Correct. Why? Because the basin-wide warming, what you see, is a response of ENSO, El Nino. Okay, but even IOD, that in fact, this is a Chayandani's PhD topic. So the IOD time, if you see, that slides I have removed because Chayandani is already there, so I removed it. See, if you see that, the IOD can also induce a basin-wide warming, or see, the basin-wide warming sustains even after the El Nino decays because of the IOD force.
Okay.
So what you see as a first mode is a contribution of both El Nino and IOD. Whereas the IOD signals, what we see, since it cannot sustain for more than 2 seasons, the variability explained in total is less. But if you see only September, October, November months, and see the variability, that then the IOD variability will be the most dominant. This is covering the entire entire months.
Now, are these things practically put in operational use, or can it be put?
Yeah. So this all can be. See, yes. See, I'll show you some. Okay. Anyway, I don't want to cover because the students will get confused.
No, I just wanted to know. You don't have to show. I just wanted to know whether they have already put such things in the operational.
Yeah. See, now I'll show you.
You have noticed Monsoon, you say such a big impact.
Yeah. The basin warming has important role on the northeast monsoon. And see, now there are something which I'll show you that is very interesting. There was so many. I mean, these are all slides I prepared in the beginning, but then I changed. See, this is like even the CFS V2 what we use. So this is the 1 year in 1 year lead, the correlation between the observed and the model SST. So what you see, amazing skill in getting the sea surface temperature over the global SST. And if you see, this is the 2 to 5. See, because we are now currently engaged in decadal prediction. So see, that's why in that context only we are doing all this analysis. This is the 2 to 5 year lead prediction. See, this is predicted 2 to 5 years in advance. So you can see the skill of the Indian Ocean SST. So these all have large prediction values. See, now in the decadal prediction I'm talking about. Now see, now like a climate model, like an earth system model. See, I'll show some skill of earth system. This is the lead. The skill from the earth system model. See, like this is the 2 to 5 year skill, and this is the 6 to 10 year. So you can actually have the models have the earth system model has skill up to 10 years. See, that is a point. Not only on SST, you can also see here on sea level. This is like a sea level. This is a 1 year lead, and these are 2 to 5 years lead. See, like the sea level has 1 year lead, 2 year lead, 3 year lead. So the correlation still is significant up to 2 to 5 years for sea level prediction over the Indian region. So these are all going to be put in place because the ministry now we are working on the decadal prediction. So we need to issue the decadal prediction of Indian Ocean and even the monsoon. See, monsoon also I'll show some skill. So like this is SST skill, the Indian Ocean. See, for example, this period, see the prediction comes very almost accurate. See, prediction starts from for example 93, 94. See the prediction. See prediction, and the black is observation, and the red and red, the colors are predicted. See, it is predicted from here. See, it's prediction, simple prediction. Predicted from here, the entire cycle of SST. So it comes. So many years. So we are. This is the current system. We are improving it actually. So like in Nino and even many indices, and you can also. I have see like a air temperature. See, this is the like a scale of air temperature. See, these are global and these are central India. See that the colors are predicted 10 years ahead. So you can predict to a large extent. Now this is air temperature prediction. See, it's a rainfall prediction. See now we know the skill of models in predicting rainfall 1 season ahead, but now we are trying to predict 1 year ahead. See, this is a skill. You cannot expect a very good skill, but still there are skills. See, this is 2 to 5 year skill, especially over the western region. There are skills. This is 6 to 9 years skill. But of course, these are all with a model which where the monsoon rainfall is not really so great. But if we can improve, we are improving the model. So if improved model can actually give us good good skill in getting air, especially air temperature and sea surface temperature. Actually, we are working on that. That is our the current project.
What is the resolution of this model?
This is about so T126. T126 for atmosphere, if you are talking about.
Okay. Okay.
T126 about 0.9 degree, slightly less than 1 degree resolution. Yeah, but people have shown that if you have, because in CMIP, because this type of experiments are now available in CMIP also. CMIP is also WCRP. They have initiated the decadal prediction effort. So they also show that the finer resolution models, like 0.5 degree models and all, the high resolution models are having better skill. I don't know. I have a figure on that. Yeah. I removed. Oh, yeah. So I removed the figure. See, somewhere I initially put the figure of the higher resolution model of CMIP 6. So showing they had the skill up to even 10 years, because our model has skill up to 2 to 5 years, but 6 to 9 years the skill goes. But their model, I mean, the high resolution model, some of the models, they have skill up to 6 to 9 years.
Okay, thank you.
Yeah. Actually, I will be very happy if students ask questions. That's I'm always, I will be happy if satisfied only if students ask some questions, because then
I'm sure that some students will have questions to ask, right?
Yes, so please go ahead and feel free to ask anything.
Yeah, should I close the PowerPoint? I can even stop sharing and then.
Yes, sir, but maybe they have any questions from the slides. So.
Yeah, okay, then we'll keep the slides. Okay, fine.
Yeah. So go ahead. Any one of you, any questions?
Hello, sir. Good afternoon.
Sana?
Hello, sir. Am I audible?
Yeah.
You are audible.
Sir, I have a doubt regarding CMIP 6 model. Like, how efficient the models are in predicting sea level in climatological compared to every month, how well they can capture this?
Yeah, I may have some slides to show that. Okay, I'll show you that. Yeah, see, this is the sea level variability. Okay, these are the sea level. I mean, if you look at the Indian Ocean, this is the sea level variability. You see a lot of signals in the southwestern tropical Indian Ocean. Okay, so now, okay. See, this is the sea level variability. Oh, okay, this picture maybe yeah. Okay, yeah, this is what you are asking. The sea level variability in the observations. See, this is simply standard deviation. Okay, the standard deviation of the sea level. If you see, you can see there are regions in the Indian Ocean, there are regions in the Western Pacific, Eastern Pacific, etc. So now, these are the models. You can see. So what you can see is there are many models which are representing what you see in the observation. This is the observation, and these are models. You can very clearly see that models are able to get the observed variability very nicely. And this is the bottom one. This is the decadal variability. See, the decadal variability signals are not exactly following in the same boxes. So you can see some large signals in the North Pacific, and there are signals in the Equatorial Pacific and South also, and the Indian Ocean also you can see. And these are the decadal variability in different models. You can see the models are able to get the decadal variability also to some extent. Now, the next question is the same models, what they project. See, this is the historical, for example, is the historical, and these are the projections. Projections for the 21st century. Okay. See, like the projected one, like in RCP 4.5, for example. So what you see is almost similar pattern. The change you see here, the changes. So there are significant increase in these variability, in the interannual variability over these regions. There are reduction of variability in the Indian Ocean. Similarly, you can see decadal. There are, reduced decadal variability over this region, but there are increased variability over the western coast of India, especially the Arabian Sea region. So there are, so basically the models are able to capture. This is the best figure to compare. So did it answer your question?
Yes. And also one more that so when I have tried pattern correlation of sea level rise in Indian Ocean for the time period 1993 to 2020, I could find a pattern. Every model show similar pattern. And one thing I have noticed that during the La Nina years, the correlation is very low. Other times, correlation is relatively 0.6 or something, but it shows a high dip during the La Nina years. So, what can you tell about the extensive models to capture La Nina and all?
Yeah, actually, the CMIP models have problems in getting the El Nino and La Nina cycles. So the exact cycle is not reproduced in the CMIP 5 models. So that could be responsible for higher correlation what you see during El Nino years and lower during La Nina years. Yeah.
Okay, sir.
Okay. Thank you. Well, nice questions, actually. Good questions. Yeah, I think you are working for your project on this one, this sea level. Oh, okay. Okay. All the best.
Okay. Anyone else?
Yeah, ma'am.
Abhi, yeah.
Sir, actually, you mentioned that when we are doing the PC time series analysis, the graph which you showed between IOD and PDO, we don't have a specific correlation after 1980. Like any speculative reasons for that?
Yeah, actually, I was not showing that dipole mode. It is the basin-wide warming. So, okay, what I was showing, it's all under decadal time. Okay.
Yes.
Yeah, this is yeah, this is what you were referring to, right?
Yes, sir. Yes, sir.
Yeah. See, this is a problem which is we don't really know the solution, but we have examined some of the aspects, and I can give you some points. Like so one important point is these are the different indices. The black line is the equatorial Indian Ocean winds, and the blue one is the low-level jet, monsoon jet, and this represents the masculine wind pressure, and these the light blue is the rainfall over Indian landmass. And what you see is in a decadal time scale, all these had sort of a multi-decadal variations, and only you can see in the interannual time scale we know that low-level jet and monsoon has very good relationship, but in the decadal time scale, if you see the black and the that means equatorial Indian Ocean winds and the precipitation has better relationship, and they all show some sort of a decadal signal. See, the multi-decadal nature has weakened, and rather, I mean, instead, so you get more of a decadal relationship. So the weakening of that means, so possibly the Indian Ocean is warmed up to an extent where it can control the other modes of variability, so that the multi-decadal nature of modes like AMO and PDO and its impact on Indian Ocean is weakened, and the local, the Indian Ocean, the modes is strengthened, so that that the decadal nature is dominating after the 90s. So this is one thing which we have seen. See, another one, you see this period, for example, the 94 to 94, when the shift what we are seeing. So here we try to find the correlation with with the Pacific winds. So what you see is, prior to this period, the Indian Ocean responded to the Pacific features very significantly. Whereas after 93, in fact, things are opposite. The response of the Indian Ocean to Pacific winds. So these are like simple correlation with the Pacific winds, equatorial Pacific winds. So you can see the drastic changes.
There was a call in this number.
Pardon? See,
Okay. So the seminar went beyond its schedule.
So you can also see the equatorial Indian Ocean winds. You see the decadal nature of the winds and its relationship with the monsoon. So one thing, there is strong coupling between processes in the Indian Ocean in the recent years, like masculine winds, masculine the pressure, the rainfall. See, all they have strong the coupling in the recent years. So that may be responsible for the weakening of the relationship with the other modes of variabilities. Okay, I know these are very complex questions, so we are working on that. I think maybe in a year or two we will be able to. One of my students is still working on this problem, so yeah, I can't say more than this because we don't really know that.
Okay, sir. So in long scheme of things, if we are some parameters in the initial ways were correlated, we can't say for sure that they will be correlated for a longer period of time. Is it so?
It is not because of that actually. That is true, but this case, it is the multi-decadal nature, because see, we know the Indian Ocean has been responding to all the multi-decadal variabilities such as AMO, PDO. This is all well known. But what happens now is that the Indian Ocean is not responding well to these multi-decadal variabilities. Rather, it shows a dominant decadal variability. So this cannot be explained by the well-known the modes. Yeah.
Okay, sir.
This could be a very challenging problem also, because you need to understand what is happening. See, something, because the equatorial Indian Ocean is becoming very active in the recent years with its dominant structure.
And son, if like during the lockdown, the last year, there would be drastic changes in all of the parameters that's what like the emission of aerosol and those all things drastic. So based on that, for the upcoming years, can we have a proper model, or we should be reconsidering our models?
Yeah, this is a very important question and a challenge to all the modelers and the meteorologists. There's some impact on the air quality, etc. People have seen impact on the health and other sectors. People have seen, but what on a climate scale is a concern now, because see, all these things are going to get affected because of this. Because you see, like the projections, so these are all projected in a completely different the socioeconomic impacts taken into account. But now with COVID, I think the entire world has changed. The working culture has changed. So all these may have impacts. Maybe you are right. I mean, it's very complex and tough time for the modelers, climate modelers in general. I agree with you. Right. Yeah, it could be. It could be, because if this trend like a lockdown or this work from home concept continues for a long time, then all hypotheses we currently have need to be revisited, right? But the models as such need not undergo any changes. Only the forcing we need to modify, because that is not going to change much. But what external forcing? See, the external forcing might be reviewed and revised, right? Yeah, that's a concern. Yeah, are you convinced or no? But anyway, question. See, this question, your question cannot be, answered in a simple way. We really don't know this. These are only speculations. We can only speculate. But yeah, it's a very good question. Yeah.
Okay, so maybe we take one last question, sir, because our office vehicle will leave.
Oh, okay, I know. Yeah, okay.
Maybe last one question, if anyone has any question.
Yes, I have a question, sir. So we can see that the strong El Nino intensities are like increasing as the years go on. So is there any connection between the intensities of El Nino and climate change? And
people say that, yes. Yeah.
So is it a major factor in considering the strength of an El Nino, or like what are the major factors on the intensity of El Nino?
See, that is it's again a problem which is not really known, because the sort of the strength of your winds, strength of your the waves, so all, and how much heat was accumulated before. Because I told you the El Nino is a process of removing heat. Though we see there is warming. See, El Nino time, the heat stored in the West Pacific is removed, or it is taken towards eastern poleward. So this is actually discharging phase. So now the strength of your El Nino will depend on how much warm water was accumulated in the tropical or Western Pacific.
Okay, so because of higher warming, like with global warming, and also we can say that maybe it is in that way, sir. Climate change.
It can. Directly. It can. Right. It can.
Okay.
Because if you see the 2015 is a very strong event, right? So, yes. Prior to that, the PDO phase was in a negative, and there were frequent La Ninas, and the Western Pacific was storing a lot of heat. So it is expected that the El Nino following will be very strong. So that is what the amount of heat available in the Equatorial Pacific determines the strength of the El Nino in general. But again, it's again associated with the air-sea interaction processes. So if anything weakens, so it can weaken our strength. Yeah, that's what happened in 2014. one easterly burst, and then the El Nino disappeared.
Yes, yes. Thank you,
Okay,
sir.
okay. Anyway, nice to speak to all of you. All the best to all of you.
Thank you so much. Sorry, sir, we kind of are a little bit.
No, I was enjoying only. I was enjoying. No problem.
But yeah, it was a good interaction. Thank you so
Okay,
much,
okay,
sir.
okay.
On behalf of.
Okay, thank you. Yeah, thank you for the invitation.